Good evening or good morning, everyone, depending on which part of the world you're in. And thank you for joining us in another webinar from Quantum London. So for those who are new here, just a couple of words of what we do, who we are and what we do before we get into the actual content of the meeting today. So we are a group of people who are passionate about this the quantum world, quantum computing more specifically, and quantum technologies more in general. The group has been set up about 1 year ago, just with the objective of looking on how these technologies which are coming our way are going to impact the business world. So what are going to be the practical applications, and what will it mean for our industries, our businesses? And what we do is we started with some in-person meetings in London last year, basically. First part of this year, and then as we know the pandemic kicked in, we moved into this online format, and we run a series of webinars with experts. We try to connect experts and people who are curious about the technologies together, and share knowledge and build a shared understanding around these topics, as well as some podcasts which you will find online through our social media channels. So today we are going to talk about quantum networks. I'm going to introduce the speakers in a second. I'm pleased to have Craig from our Quantum London community. He will help me moderate the conversation today. And without any further ado, let's go straight to the conversation for today. And I would like to introduce Aitor Villar. He's a quantum engineer at SpeQtral. So today we'll be looking at the quantum networks, and more specifically the use of nanosatellites and whether they are a suited candidate to enable cost-effective global quantum networks. And he will also talk to us about what his company is doing. He has written a paper recently, and we'll share some of the findings from the paper. And I forgot to mention, so this meeting is being recorded. Just please be aware of that. And you have a chat on the right. So if you have any questions for our speaker, please feel free to use the chat on the right-hand side, and myself and Craig will moderate those questions and ask those questions to Aitor. Again, I think I said enough. I will just invite Aitor to come on screen, maybe introduce himself, and then start giving us an overview on what quantum networks are and what he has been doing in this space.
All right, thanks. Thanks, and hi everyone. Hi Craig. I'm Aitor Villar. I'm based in Singapore, currently working at SpeQtral as a quantum engineer. My background is on telecommunication engineering and quantum physics. I did my PhD at Center for Quantum Technologies in the National University of Singapore, basically building quantum instrumentation for space. And I'm very happy to be here and be part of this webinar series. So thanks for having me.
So do you think you could start by giving a bit of introduction on what are quantum networks, specifically satellite-based quantum networks? Why are they used, what they are, and what they are used for?
Sure, absolutely. So one can think of quantum networks as the networks that we have nowadays, only that the nodes that make these networks are actually able to manipulate, generate, or transmit quantum information. So whereas classical networks will deal with bits of information, quantum networks will deal with qubits. Now, why is this interesting or relevant? As it turns out, there are many quantum properties of quantum objects that could be harnessed for our advantage in different fields, particularly in the field of cryptography for securing communications. Also, different applications will deal with secure authentications, or one could even think of the future quantum computers being all in the cloud, interconnected via a quantum network or a quantum internet. So indeed, there are many advantages to be harnessed once a quantum network is indeed deployed.
a bit of a chart, and you mentioned that one of the applications of the quantum network using satellites is the quantum key distributions, which is something we touched briefly on a previous webinar. But will you be able to give us a bit of an explanation what it is, how it works, and why it's superior to other technology out there?
Sure. So quantum key distribution is arguably one of the most mature quantum technologies nowadays. So QKD sets up to exchange secret keys between two parties that can later on use these keys to secure their messages and therefore communicate securely. Now you mentioned about QKD with satellites. This is something that maybe I'll go more into detail later. But QKD networks are already implemented on Earth. Just that if you really need to span global distances or continental distances, that's when the space segment plays a very important role. This stems from the fact that entanglement is mostly carried by light particles, and these particles travel through either optical fibers or free space on ground, and that's the distance, the maximum distance that they can achieve at decent rates are a few hundred kilometers. So if you really want to span communication distances, let's say linking Singapore with London using QKD, as it is right now, as the state of the art of the technology stands right now, space to enable the space segment really seems like the only feasible way to link two distant countries. I think you are muted, Em.
This one today, actually was now. So experts, but if I understand correctly, so you have satellite in space, or maybe a network of satellites in space to build some redundancy, and you use satellites to send photons down to Earth, and these photons represent a quantum key, which can be used then by two different parties to then exchange a secure communication through traditional channels, right? Okay. And I think we were discussing yesterday again whilst preparing for this call. So, what are the limitations of this technology?
Right. So, once you start implementing quantum technologies, just by definition, you're working with quantum objects. These objects, you're dealing with single photon objects, with single particles of light, and they just so happen to be very delicate. You don't want to mess around with these particles. If not, you will lose its very nice properties. And this goes linked all together from the sources that generate these single photons to the detectors that detect these single photons. And this just goes to say that attenuations or losses in your quantum channels, whether it is over optical fiber or free space, that's a very limiting factor of these technologies, and it's a fundamental limit. There's nothing you can do about it.
Mm-hmm.
So you need to re-engineer, your sources of entanglement. You need to make more sensitive detectors that can detect even ever so lower levels of intensity. But that's the price to pay if you want to indeed harness the quantum properties of photons.
Paolo, who is the co-founder of Quantum London, is probably on a beach, I suppose, now on holidays, and is still active here in the chat. So he's asking, you say entanglement is carried by light particles up to a few hundred kilometers. Given that entanglement itself appears to defy so much of common sense, why it is limited in distance?
Well, you can just think of, so maybe I phrase that differently. So entanglement is being carried out by photons. So you can think of the photon as the vehicle of entanglement. Now, once the vehicle stops, the entanglement stops. But this is I'm talking in the physical kind of like implementation level. As we know, so far it hasn't been found yet a distance, an arbitrary distance, whereby the entanglement vanishes. So what vanishes here is the photon due to the losses of the medium it's traveling through. It's not the entanglement per se. So I apologize for the confusion.
Yeah. No, I think it makes sense. It's the photon that gets lost, not the property of the photon. Okay. I think you have some few slides for us, which can maybe help us understand a bit more around what SpeQtral is doing in the space, what's the value proposition, what is the state of the art at the moment on this topic. So let me go and share those. And you do have control of the screen now, so you can move freely.
All right, so maybe just a few words before I get into the slides. So SpeQtral is a spin-off company from the Center for Quantum Technologies at the National University of Singapore, and basically we are set up to build, as you know, in the supply chain, we position ourselves as a technology provider, where we focus our efforts in space-based quantum instrumentation. So we have the knowledge, the know-how on how to build these instruments that can live in a satellite, operate from a satellite, and give these quantum links from space to ground. And also want to mention that this is kind of like at this point that we are right now. Really, we come back from almost 10 years ago. In 2010, where Professor Alexander Ling set out this space program to put technology into quantum technology into space. So once this kind of like research stage was done, some of my colleagues thought it was a good time to commercialize this technology, and so I joined them last year after I graduated. SpeQtral is 2 years old. And again, we have the know-how, the knowledge on how to build these instruments. Basically, also because about 60 or 70% of our staff has some is related somehow to the CQT. So it's very nice. It's a very nice and dynamic group to be part of. So, however, these slides will cover the results of the SpeQtral mission. So the SpeQtral mission, again, was fully implemented. It's a program fully carried out by CQT. Now, however, SpeQtral has taken over the operations of the satellite. So I want to run everyone through a little bit of the history of this mission. And for that, what I'll try to do today is explain how we end up with this picture, with our SpeQtral-1 satellite being deployed from the International Space Station sometime last year in June. So just for context, a little bit of motivation. We already touched on this a little bit, but by now we know how entanglement as a resource improves and gives new capabilities for protocols or technologies in different fields. Let it be metrology, simulation, or computing. But the one we are focusing on right now is communication. So within the communication field, some applications, as we already mentioned, are quantum key distribution, quantum teleportation, or clock synchronization. We already mentioned this, but photons are typically the carrier of entanglement. So this makes QKD and different other protocols based on quantum entanglement a optical technology. And once this always happens with communication protocols, once they are demonstrated, the next step is always to increase the communication distance. So this is where, again, the limitation of dealing with quantum particles hits again. And traditional ways of doing this, whether it's a free space on ground or optical fibers, are limited to a few hundred kilometers. So it kind of comes naturally to think of the next step as space, right? So if you think of moving to high altitude platforms that can be equipped with quantum instrumentation, a brand new sort of like ecosystem of opportunities opens up. One can think of, let's say, having the detection system on space and shooting your entangled photons from the ground. This is known as the uplink configuration. One can have just the reverse, the downlink configuration, where the source of entanglement is on the space and on the satellite, and is shooting down entangled photons to the ground station. You can do this on a single or a bidirectional link, as depicted by case 3, or even inter-satellite communications, where different satellites forming constellations talk to each other, talk to different ground stations, just to build on redundancy and duty cycle of operation. So again, ideally, one would envision a network of these quantum satellites, of these quantum nodes, ready to either transmit entanglement, store entanglement, measure entanglement, and so a quantum internet will be, a global quantum internet will be possible. Now, what the SpeQtral mission set out to do was something a few steps back, but kind of like starting from the beginning. We set out to be able to create and detect entanglement while on orbit. Now, for this, what you need is, of course, a satellite and then a source of entangled photons. So today, what I want to explain is what it's inside our satellite and what is this interesting or good for. So of course, space is not cheap. It takes time, it takes money to get there, and not quite recently already. It's almost been 20 years, but Cubesats in the early 2000s made a very disruptive entry in the satellite industry, lowering costs and making satellite missions much more cost effective just by using standardized blocks. And by this I mean that you could literally go online and buy a radio for your satellite, a pair of antennas for your satellite, or the chassis for your satellite. So this is very good in terms of trying to get your technology ready and getting it ready very quickly. So these satellites, and actually I have a copy of SpeQtral with me right now. They're very small, they're very compact. This is to scale. This is 1-to-1, an exact copy of the SpeQtral satellite. So you can see how it really is not big at all. And this also lowers costs of the rocket launch. And of course, not everything is good about Cubes. There's no as Cubesats, by the way. The standard that these nano satellites use is known as Cubesat.
So what is the weight of the device?
So this SpeQtral is 2.6 kilograms. Really light. I'm not even putting much strain on it. And very importantly, there's something that you all need to know about Cubesats is, of course, it's very small. So the solar panels are also very small. So the power that you can draw from them is not that much. So this is on the downside of Cubesats. They're very nice, they're very cheap and so on, but the resources are rather low. So when you think of putting instruments into these spacecrafts, there are many considerations to be aware of, such as how much power is my instrument drawing from the satellite, how much volume am I taking on the satellite. So once we selected our spacecraft, we had to again go back to the basic principles and start designing our entangled photon source, so that it's able to meet the requirements of this CubeSat. And so here I'm showing the mission path. Yeah, sorry.
No, sorry, I was just me thinking out loud. But yeah, suppose for the device to work, it needs to be shielded from radiations and all that, right?
Yes. Well, so if you want to divide the components of the satellite between the quantum and the non-quantum, so all the satellite parts, of course, are ready to go to space. They have space heritage. On the quantum side, we do need to take care of things like, as you mentioned, radiation, vibration, thermal changes. It has to be light tight, because we don't want to flood our detectors with meaningless, stray light. And I also have with me a an exact copy of the quantum source inside the SpeQtral satellite. So we will start from here. We have our blue laser, a bunch of nonlinear crystals. So this is where the entanglement happens. And then, because I mentioned that we not only generate, but we also detect the entanglement on board, this is what we have these two arms for. Here and here, you have a single photon avalanche photodiodes that are able to detect the entanglement produced by this source over here. Again, this is about 900 grams. It has the inbuilt electronics of these chips. So personally, I was involved in the optics manufacturing of the optics building of the experiment. But then again, this was a team effort where we had optics people, electronics people, mechanical engineers. So yeah, it was a good group effort.
But a related question from the chat from Anahita. She's asking whether the device is vulnerable to space junk.
Well, we could think that, nanosatellites being small, maybe they're able to dodge debris better, but really it's very hard to say. In fact, for a nanosatellite like ours, there is no, we don't have active kind of like control of the orbit altitude and so on. So when you sort of like think of what orbit do you want to put your satellite into, there's always the launch provider will always give you an estimation of chances of getting hit by space debris, and this is just something that you have to live with.
The send is relatively cheap, so if anything happens, just send up another one, I suppose.
So funny story. Again, so SpeQtral is the kind of like the ultimate mission for our group, that where we demonstrated our technology and so on. But that wasn't like a one-shot chance that we took. Early in the project, 2013, 2014. We started with weather balloon tests where we'll put our payload, our quantum instrument on a weather balloon. We will release it. It will reach about 40 kilometers altitude and it will burst afterwards. So we will be collecting the data throughout the whole trip. Once we were confident after the weather balloon test, we piggyback our unit, or a kind of like a simpler version of it, but just to demonstrate most of the components in our unit, because really 10 years ago, 5 to 10 years ago, pretty much no one had flown any of these lasers or crystals or single photon detectors. So there was a lot of technology readiness level acceleration here. And in one of our trials in 2014, we put our payload into a collaborator satellite, and the rocket literally exploded shortly after liftoff. So, it's just once you try to tackle space, things like this can happen. But funny story, we recovered that satellite, and it was actually intact after the explosion, and we were able to run our payload, and there was a paper on it, so people can look it up. I think the title is "The Quantum Source That Survived a Rocket Explosion," something like this. Yeah. So it really was several iterations before we reached to, SpeQtral, and we managed to demonstrate entanglement on orbit.
So sorry for the interruption. I will let you carry on with the presentation. Just also conscious of time. I think we got a few questions in the chat as well. So
I'm almost halfway.
Back to you.
So okay, so this is the quantum payload. Some close-up shots, but we are already seeing the thing live, so no need to go through this in detail. So what I wanted to mention is, how do we know that quantum entanglement is actually being generated here? So the figure of merit that we use is something known, sorry for the technicality, but the violation of the Bell's inequality. But basically, in layman terms, we look at the correlation curves of the coincidences between these two detectors. So we generate the entangled photon pairs, we split them up by wavelength, and then we set up different polarization settings in the detection arms. And basically what we want to see is if one polarizer, which is nothing but just a filter, it's set at vertical, and the other polarizer is set at horizontal, we would like to see a zero count. Basically, this is a very good, this will tell us that the interference is very good. Once these two polarizers are parallel, we would like to see a maximum of this interference. Then you are able to compute the contrast of this correlation curve. So it's basically, your minimum, you want it to be as low as possible. Your maximum, you want it to be as high as possible. Then the higher this contrast, the better your entanglement quality. So basically, this is the figure of merit that we are after. Basically, a set of curves, and this is pre-launch. This is all in the laboratory, and very quickly, just the journey of SpeQtral. Of course, it was built in Singapore over the years, integrated in Japan at JAXA, the Japanese space agency, last February 2019. A few months later, we got sent to the US for the rocket launch in Antares vehicle, which was SpeQtral was part of the resupply cargo mission. Reached the ISS several hours later. Then 2 months after that, 17 June, from the ISS, from the Kibo module, the Japanese module in the ISS, SpeQtral got into orbit. So this is how we made it to this picture that astronaut Haig, I believe, very very kind of took a picture of SpeQtral as it was getting into orbit. And shortly after orbit injection, we started operations. Basically, there were a couple of weeks or characterizing the thermal environment that SpeQtral was seeing at around 400 kilometers altitude, and see where the sweet spot in terms of temperature was for us to switch on the experiment. And I think it was a few weeks later when we knew it was safe to operate SpeQtral. We got very nice results that proved that entanglement was there, was preserved, working as nominally, and even more, we managed to not just the sweet spot, but a range of 5 to 6 degrees Celsius. We could identify good ranges of performance, and basically it was a success. The results were published in Optica last month in July, and that was a great result. And again, I want to thank, of course, the SpeQtral team from CQT, led by Professor Alexander Lin, who made this happen, and also our international collaborators, Daniel, Douglas, and Christoph from Glasgow, Australia, and Switzerland, and now the SpeQtral team for carrying on with the SpeQtral operations since November 2019. I'm very happy to report that it's been more than a year in orbit, and still radiation hasn't burned our detectors. The laser is still lasing, and entanglement is still being produced as we speak. So that's really really great news. And with that, I'm open to answer any questions.
It's fascinating, great story there. And we do have a number of questions. So I will start with the most fundamental one, and then Craig, please, feel free to jump in and help me moderate with the questions. So, question from Jail: how is quantum networks related to 5G networks? Is it quantum network going to replace it once it gets scaled, or is it more about the security and the networks can work together?
Wow, interesting question. So I believe they don't have much to do with each other. We should take 5G as the high-speed, kind of like mobile communications. This is going to be. I mean, it's great. It's going to be really, really good in terms of increasing the bandwidth of, for the users and for applications. I think quantum networks are set up for a totally different purpose.
still use quantum networks to generate the encryption keys and then use 5G to transmit those data fast and encrypted, right? So maybe all the two work together.
So basically, let me also emphasize on quantum networks are not a substitute to the classical networks as we know them right now. Apologies if I didn't make that clear before. Basically, it would just be a top layer into your classical networks where whenever an extra level of security is needed, or you really have quantum computers on the cloud and you want to link them up. That's what quantum networks are really good for. Now, the same way quantum computers are not going to replace classical computers, quantum networks are not going to replace classical networks. So there are different. They don't have to do anything with each other in terms of the level of applicability, if you want. But yeah, it's not that quantum networks are going to completely take over and every other network is going to be quantum.
No, thank you for clarifying. Craig, any interesting questions in the chat?
Yeah, well, I think there's. Anita, I took one of mine, but we've also got this question from Jail on how quantum networks related to 5G. I just wanted to add to that a little bit. Can you give us any insights, perhaps, on this Apple project to enable where this kind of cross-connect or crossover between 5G and direct satellite chipsets on new mobile handsets are being connected?
Oh, interesting. You say Apple? Nice.
Yes.
Oh, well, I think you know more than me. It's the first time I hear about this. So basically, they're putting chips on mobiles and linking this with 5G networks, that you said?
Yes, and so there's a direct-to-satellite or a ground-to-satellite type of Wi-Fi connection being established and interconnect with 5G. That's the current chipsets that are going on to the devices, but they're not quite enabled yet.
Interesting.
I didn't know if you were able to give us any insights on that, but that may be where Jail's question was coming from.
It could be. I'll definitely need to read up on that.
Okay, so I mean, one other piece. I don't know if there are any more questions, but please get them in as we're going to be limited for time. But you're requiring on. I think I really quite like the idea of saying, look, could you just take our box up into space and throw it out the window when you get to this particular place? How is command and control figured out? And I mean, who ultimately takes control of your mission, or do you just sort of have command and control as a service in the cloud that you can just log in and start to take over your mission? How does that work? So
are you asking from the very moment where the satellite gets into orbit, and then what happens? How do we talk to the satellite and so on?
Well, yeah. I mean, I imagine it takes a fair number of meetings to get to the point that you're actually deploying your payload. But when you get there, and what happens after they let it go? I mean, you take over at that moment?
Sure. Yeah, so basically what happens is the satellite goes into orbit, and when it's getting deployed, the antennas that are still sort of like tacked into the satellite. At some point, these antennas will deploy and will establish a radio link with our ground station. Now,
so it's your ground station that you connect to directly?
Absolutely. So we have two ground stations, one in Singapore and one in Switzerland with Crystal, one of our collaborators. And basically you establish this radio link, and you can calculate what times of the day you're going to see Spooky passing over your ground station. So basically, on average, you will get 6 to 7 good passes over your ground station, and each pass will give you in between 5 to 10 minutes of radio communication. So once we set up the radio link, we are able to send commands to Spooky, talk to the microprocessor inside the electronics, somewhere here, this guy over here, and the satellite can tell this unit to switch on the laser, go to 50 milliamps, start recording APD counts, set your polarization settings, horizontal, vertical, diagonal. So it's all sort of like automated, and we are in complete control of the what happens to the payload. Now, things that we don't have control over is the altitude of the satellite. We don't have active, thrusters to, boost up the altitude of SpeQtral, again, because it's not cost effective. Cubesats are cheap for a reason, right? But yeah, other than this, we are totally in full control of SpeQtral.
Well, I mean, I love the name Spooky in the first place. I think that's tremendous. And I'd like to know who came up with that. But I mean, going a little bit further on, it sounds to me as though you've got a limited window at different points in time in different orbit locations where you can take your data dump and replace it with your next mission packet, I guess. Is that right? Is that how it works?
Yeah. So the first question, the great name was, from CQT. I believe it was the outreach department. They were doing an amazing job.
No, it wasn't your idea.
Unfortunately, no. I can't check. I voted for it. I voted. I said, this is the one. Yeah. But so the next step is, again, you mentioned there are limited windows of time where you can talk to your satellite, do meaningful experiments, or exchanging your key rates. So QKD, and let's just talk about QKD from space. So of course, with one satellite and one ground station, you can't possibly offer on-demand service. You're going to be limited at some point, depending on your demand. But a couple of things. You can always buffer your key. So basically, you could run every other orbit. You can run your experiment, produce secret keys, QKD keys, store them, and just continue, just repeat. So whenever there's a need on key supply, that's you take from your buffer. Another option, perhaps, is come up with constellations of these satellites, and you could imagine 10, 20, 100 satellites giving coverage to different ground stations, and this will definitely improve the throughput of your system. So I agree. If you just think in terms of single satellite, single ground station, it's hard to envision a direct sort of like service that you could provide 24/7. But there are solutions to that.
Questions in the chat, more from a commercial and status of the market angle. So Paul is asking, lots of countries are talking about wanting to take the lead in various quantum technologies. So based on the fact you are in Singapore, the question there is, can you tell about, what's happening both explicitly in terms of public statements, also implicitly in terms of investments, research, education? So who is leading? Is it militaries, universities, tech firms? What's the status?
Well, the Singapore ecosystem is, in terms of quantum technologies, if you want, I think it's a very healthy ecosystem with a very good balance. Of course, everything started from fundamental principles, so you wouldn't hear of a company like SpeQtral back in 2005, 2010, but rather what happened back then was groups like the one I did my PhD at with Professor Alexander Ling very early on identified the potential of this technology. So research programs were put in place, they were funded, and I'm part of this. I'm kind of like a result of that experiment. I moved from Spain to Singapore to pursue this PhD, and now you are starting to see spin-offs coming out, whether they are public or privately funded is kind of like up to the spin-off. But still, recently, a couple of weeks ago, there was a what they call quantum engineering program set out, which is again a very nicely put program for I believe it's undergrads and graduates, if I'm not wrong. But basically, just they're making sure that still at the university level, there's proper research being done, and at the same time, it's very, I wouldn't say it's very easy, but it's definitely feasible for people with enough very enthusiastic about these technologies to seek for private funding, public funding, set up a spin-off to either do quantum computing or quantum algorithms or quantum communication like we are. So I think is indeed a very healthy ecosystem, the one that we have in Singapore.
Craig, for sharing in the chat the link about that news around
Yeah,
Apple
appreciate
using
it. I'll take a look.
technologies. Check it out. Thanks. And I will invite the audience, if there are any other questions. We are about to wrap up. Put them in the chat. We have just a few minutes left. And I wanted to ask another one from Paolo, which is a team which comes, every meeting we have similar kind of conversation. So he is saying, clearly, all of this is a result of several years of hard work. If you look back 2, 3, 5 years, did you believe we will be at this point right now? And then taking that point forward, how rapidly do you think this technology is developing? Will we be in 10 years at the point where we can hardly manage now? So how does
it's a very interesting question. For me, being really in the laboratories and working on this technology, I think the timing was just right. Technologies need to mature. As I mentioned, in 2010, 12. No one even thought of putting, a blue laser in a small satellite. So there was a lot of work to be done. I was really surprised by relatively surprised by the Misha satellite, the Chinese satellite that very impressively, took the #1 position in many records and in many groundbreaking works. So that sort of surprised me how quickly, relatively quickly, they put everything together. But I think the timing is right. There is efforts put in place in the right direction, and I think the 10-year mark seems a little bit too far off for me. Maybe I'm just too optimistic, but I really think people are working in the right direction, and it's more than 5 instead of 10. But definitely, hopefully, we will see happen. We'll see happen.
Thank you. That's great. I don't think we don't have any other questions at the moment. So, yeah, I think we can wrap it up here. And Aitor, thank you so much for being with us, spending a bit of time with us, talking about what's been happening in the space and about your work. So thank you, really appreciate that. And thank you, Craig, for helping me out today. Let me just put back on screen the presentation. So at the bottom there, you see the meetup. We have a number of similar events running in the next few days and weeks, so please check that out. What else did I want to say? If you have any other topics you would like us to explore as a community, please do get in touch and let us know. And once again, thank you, Aitor, very much for your time today. And we hope we can keep the conversation.
Thank you, Aitor.
Thank you so much.
Thanks
Have a good day.
Bye.
And to your team, good luck with your
Thank you
future
so much,
missions.
Craig.